Okay, so now we are concluding this topic of modem design, and specifically we are looking at how the simplified model that we started out with, where all it is very powerful in capturing the essence of the design problem, and where it falls short in representing the detailed complexities of the design. And what we can say at this point is that once we take into account the effect of pulse shaping operation and the effect, the corresponding effects in terms of the intersymbol interference, adjacent channel interference, and so on, uh, we can say that we have pretty much entirely captured the not only the concept but also the details, the important details of this digital domain design and implementation of the communication modem. Uh, if I were to say the main topics that we still haven't addressed, uh, then those would be related to the timing estimation that is required at the demodulation side. So apart from that, one can say that uh, we have captured the digital aspects of the modem design pretty well. We have spent quite a lot of time in understanding the operation of this channel encoding and channel decoding blocks. Okay, there is a typo here. This should be decoder instead of encoder. This also should be decoder instead of encoder. I'll correct it in the slides that I post on our Google Classroom. We have spent time in understanding the source encoding and source decoding. We have spent some time in developing the mathematical model of sampling a continuous time signal. And we have looked at the Nyquist theorem, which says that um, a signal which is band limited to capital B hertz can be sampled at a rate which is at least as fast as B samples per second, and then such a signal can be perfectly recorded by D to A converter. So A to D and D to A mathematically can be inverses of each other. So we spent some we have understood the mathematical model of A to D and D to A blocks. Uh, what we have also done in at least theoretical sense is the operation of this frequency upconversion block that is shown over here. And this we did by means of the modulation theorem of Fourier transform. So in this last portion of this presentation, I wanted to complete a study of the frequency up conversion and frequency down conversion. And along with that, I also wanted to complete the earlier discussion or earlier model that we had, in which we took a binary phase shift kit signal, which was one dimensional, and we made it two dimensional by introducing a quadrature component, and we called it SI and SQ. And at that time, we said that we don't know right now how to create a quadrature component which is conceptually at 90-degree offset, at 90 degree with respect to the in phase portion. So that is something that we had postponed to a later part of this presentation, and that is what we will discuss in this remaining slides. Okay, so first of all, why do we need to do frequency up conversion at the transmitter? The reason is that although ultimately we are interested in transmitting the symbols which carry our bits, as we have seen by that bits to symbol mapper, The problem is that the symbols by themselves cannot travel far away, whether it is rectangular pulses or whether it is raised cosine pulses. Uh, those voltage levels are difficult to push far apart, whether you are trying to communicate over a cable or whether you are trying to do wireless transmission over several kilometers, or in case of satellite links, it will be several thousands of kilometers. And so that is why the frequency upconversion is needed, where we take those symbols and we use those symbols to modulate the either the amplitude or the phase or both, amplitude as well as phase, of a sinusoidal carrier. And the reason why this sinusoidal signal is called a carrier is because it has to be thought of as a truck or a goods train. It's like a carrier uh, of your packets, and it takes your symbols, which are the actual entity of interest, and it transports them to to a destination which may be far away in terms of distance. Um, and then once the signal reaches there, then the carrier portion gets stripped away, and you get back the symbols, uh, the actual symbol waveforms. How that happens is what we are going to look at next. Uh, the reason why we are going to be using sinusoidal waveforms is because all of the electromagnetic transmissions that happen through the antenna and the signals that therefore propagate well in the atmosphere and over the cables are all sinusoidal in the nature. So that is the most important reason uh, why we'll be focusing on the sinusoidal waveforms. Plus, these waveforms come at a specific frequency, which is known as carrier frequency, which we have earlier called f of c. And that f of c can allow us to place our signal spectrum in the desired portion of the frequency domain. And that allows us to create channels, so-called channels in the frequency domain. When you tune to one FM channel or one TV channel, essentially you are looking at that particular carrier frequency. And finally, there is a detailed design aspect in terms of the carrier frequency and how it relates to the antenna size and the path loss, and ultimately the overall system design and overall system performance depend a lot on the choice of carrier frequency. And although this may seem like a little bit of a detailed aspect, what I would say is that the 5G systems and the next generation systems that are currently being designed, there one of the proposal is to use a particular carrier frequency which is very large, and there are a whole lot of ramifications in terms of antenna size, path loss, etc. That the researchers and the designers and the engineers are currently working with. And that choice of carrier frequency proposal is called millimeter wave communication. Basically, the wavelength is such that it's down into millimeters, and the corresponding carrier frequency is in more than several tens of gigahertz. So this trade-off is a very integral component of our 5G, upcoming futuristic 5G systems. Okay, now let us model this frequency upconversion and downconversion uh, by uh, three different mathematical equations, which are, on the face of it, they look different, but actually they are completely equivalent. Uh, these three equations refer to the same exact signal. So the signal which is actually getting transmitted can be written either in the quadrature notation, complex envelope notation, or magnitude and phase notation. This also can be related to the complex numbers. The complex numbers either have a Cartesian representation, they also have the polar representation, magnitude and phase, or they can be looked at entirely. The complex number can be just considered as a whole number, a complex number. And so that is the analogy between these three different representations. And this is where our in-phase and quadrature components that we have earlier uh, studied for all these different modulation schemes, this is where they come to, uh, they come into effect. So in the quadrature notation, the transmitted signal is SI times cosine of the carrier minus SQ times sine of the carrier. Okay. Uh, what are SI and SQ? These are the coordinates of our constellation diagrams. Remember all the constellation diagrams that we had looked at? First of all, for BPSK, SQ is always 0. Even for OOK, SQ is always 0. So BPSK is just SI times cosine of 2 pi FCT. Starting from QPSK, 8PSK, 16 QAM, etc., SI and SQs both become non-zero, and what their exact values are is what we would look up from the constellation diagrams of the transmitted symbols. The corresponding signal that actually gets transmitted, the signal that the analog signal at this point over here, is this signal S of t. This signal S of t is at this carrier frequency f of c. Now this equation, the quadrature notation, you can also get by writing it as real part of a complex number. And the complex number is the product of Si plus j times S of q, where j is square root of minus 1, times this complex exponential phasor. You can do this math. If you take the real part, you will get this equation. Okay, so the complex envelope notation is another way of writing the same signal. And this Si plus JSQ is again the transmitted symbol before it is getting upconverted to this carrier frequency of f of c. And recall that we have said that the transmitted symbol can be thought of either as a two-dimensional vector whose x and y components are Si and Sq, or it can be thought of as a complex number itself, Si plus JSQ. So that complex number is right here. And then finally, the third way of looking at the signal is what is known as magnitude and phase representation. You can write this equation here, the quadrature equation, alternatively simply as this: a times cosine of 2 pi fct plus theta, where a is square root of si square plus sq square, and theta is tan inverse of sq over si. So this is a typing mistake which I can right away correct. So this is actually tan inverse function. Okay, so that is the quadrature notation. And you can verify that if I plug theta equal to tan inverse SQ over SI, A is equal to square root of SI square plus SQ square, I'll get exactly this mathematical equation. So these are three different ways of representing the transmitted signals. Now, let us look at this representation here and see the effect of this in the frequency domain. And this is where we will bring the modulation theorem of Fourier transformation. This Si plus JSQ is a complex signal, but it is at what is known as baseband. It will have certain bandwidth. The, the actual bandwidth will depend on the pulse shape. If we use the raised cosine filter, then the pulse shape will be exactly as it is shown uh, here. For this pulse shape, that Si plus JSQ may have a frequency occupancy around 0, spreading out to some 1 plus alpha times Rs divided by 2 width. But it is, the main point is that the signal, the complex signal is centered at 0 hertz. The frequency occupancy has a width of Rs times 1 plus alpha, but the center is at 0 hertz. So, this signal, that is why it is called a signal at baseband. Baseband meaning at centered at 0 hertz. And so maybe it looks like this. Here I have drawn some strange shape. Uh, the actual raised cosine filter, as you have seen, doesn't look like this. But I purposefully drew this asymmetric shape just to show you one particular effect that comes into play in our model. So I made this side little bit tilted compared to this side, which is vertical. So this is the spectrum of the complex signal after pulse shaping. Both the in phase and the quadrature symbols have been pulse shaped. There is a pulse shape for Si, pulse shape for SQ. And the polarity and the actual voltage level of Si and SQ comes from the constellation map. Now, in the complex envelope representation, we take this as multiply by exponent of j2 pi fct. But that multiplication in time domain translates to convolution in frequency domain, and the convolution is with a direct delta impulse located at f of c. And therefore, the effect in frequency domain is that of a shift. Instead of 0 hertz, due to the modulation theorem of Fourier transform, Si plus JSQ, after it gets multiplied by this exponential signal, complex exponential phasor, the exact same signal just gets shifted, and it is now in the frequency domain. It is located at the carrier frequency where we want it to be located. Now, the last thing is that this is not really the actual transmitted signal. The reason is because this is a complex valued signal. The transmitted signal cannot be complex. There is no way to transmit this j, which is square root of -1. So up to this point, it is all mathematics. But the actual transmitted signal, which is just a combination of sine and cosine after they get multiplied by Si and Sq, is actually the real part of this signal. Now, there is one other property of Fourier transform which was given to you in the reading assignment, which says that a signal which is real valued in the time domain, meaning it has no imaginary component, a signal which is real valued will be complex conjugate symmetric in the frequency domain, which means that there will be a symmetry in the frequency domain. Whichever shape the signal has on the positive frequency side, on the negative frequency side it will be a mirror symmetry. And so therefore, when I take, as it is shown here, when I take the real part of this signal in the frequency domain, the effect is that I get a mirror image of the positive frequency axis at negative f of c hertz. And not only that, I get the mirror symmetry, but the amplitude becomes half of this amplitude, which I have tried to show. If you can see, this height is roughly twice of this height. The reason for that is also uh, understandable, because we are taking real part. We expect to lose about half of the signal energy compared to the complex signal. So this finally is the spectral diagram, the frequency uh, representation, frequency domain representation of a transmitted modulated signal. Okay, uh, now the one last thing is regarding the SI and SQ. Why did we put SI and SQ on two mutually perpendicular axes in the constellation diagrams? So that topic is what we will look at now. Uh, but we will do that in the context of frequency down conversion at the receiver. So this captures the transmitter side function. This is what the transmitter has to do. But then at the receiver, the signal which is incoming is at that carrier frequency f of c, and that frequency, high frequency signal f of c has to be down converted to baseband. So the receiver has to do inverse of this function. By the way, here I have shown a complete modem diagram, which has both the transmitter and the receiver. And this block here is called diplexer, which takes the transmitted signal and it sends it out from the antenna, and in parallel it gets the signal from the other side, the other modem, and the diplexer routes it to the receiver. So diplexer can be sort of thought of as a switch. It takes this transmitted signal and puts it out from the antenna, and it takes the received signal and it allows it to be sent to the receiver. So now we are saying that the signal that is getting received at the antenna from the other side uh, is at some carrier frequency f of c, and it has to be down converted to the baseband. The process of upconversion is represented by this diagram. What about down conversion? Well, for down conversion, essentially what we have to do is, when we get a signal s of t which can be written like this, let us say in the quadrature notation, we want to be able to extract si and sq. Because once we extract si and sq, then we will pass it through the linear shift invariant system at the receiver, which will remove those out of band noise. And then let us assume that we have some timing scheme which will select the right sample at the maximum eye opening. And then that selected sample we will send to our maximum likelihood detector based on the decision region, and it will decide which of capital M possible symbols at the transmitter side was actually transmitted. And then once that decision is made, the symbol to bits mapping table will be implemented at the receiver, which will convert that detected symbol into small k number of bits. And so you get the bits back at the output of demodulator. So now the question is how to recover Si and Sq from this S of t. So for that, what we are going to assume is that the receiver has has generated this uh, cosine of 2 pi f ct and sine of 2 pi f ct um, using its own oscillator. You see, there is this oscillator, and this oscillator is generating cosine of 2 pi f ct and sine of 2 pi f ct. It is not made very clear here. It seems like this oscillator is generating only one signal, which is going here, but really it is generating both cosine and sine. If it can generate cosine, then generating sine is not that difficult. You just put a phase shift of 90 degree, and that signal will be then sine signal, sinusoidal signal. So we will assume that that type of signals, cosine and sine, are available at the receiver as well. At the transmitter, those signals have to be there because it is only because of those signals that the signal can be sent to the antenna. At the receiver side, we need those cosines and sines uh, not for transmission purpose but for demodulation purpose. This demodulator, we want it to operate at 0 hertz. We don't want it to operate at such high frequency of f of c, which can be, as I said, in some multiples of gigahertz. And so that is where there is a need for generating cosine and sine at the receiver, and that is what we are going to assume now, that we have received this s of t, and our intention is to recover si and sq. This cosine and sine have done their job as the carrier. Because of because of them, this si and sq, our symbol voltages, symbol pulses, have traveled far and wide, but now they have reached the destination, they have reached the receiver, and the receiver has to strip off this cosine and sine and extract out si and sq. Um, okay, one thing that I am reminded of, I should mention, the reason why the names of those digital modulation schemes, phase shift keying or quadrature amplitude modulation, amplitude shift keying, etc., is because of this magnitude and phase representation. For phase shift keying, this A remains constant and this theta keeps on changing for different symbols. Basically, with different symbols, we are modulating the phase of this cosine waveform. Whereas for quadrature amplitude modulation, we are changing both A and theta. Similarly, for amplitude and phase shift keying, we are modulating not only the phase but also the amplitude of these sinusoidal waveforms. Okay, so frequency down conversion. At the receiver, in the absence of noise, again this we are saying for our conceptual understanding, if the receiver gets a signal uh, in the absence of noise, it will be exactly equal to the transmitted signal s of t, and we want to be able to recover si and sq from this s of t. And remember, we said that we will assume that the receiver has somehow managed to generate this cosine and sine signals at f of c. So let us see how it can extract si and sq from s of t using those cosines and sines. So let us consider the extraction of s of I. So what I say is that si can be extracted in the manner which is shown here. We take the incoming signal s of t, we multiply it by cosine of 2 pi f ct, and this product we integrate from 0 to symbol duration, 0 to ts, and then we need to scale the output of the integral by 2 over ts. this part, I say that it will give us S of I. Let us prove that. So what I will do is I will substitute S of t, which is this expression in this equation. And so this expression becomes this equation here. Si times cos square 2 pi f ct, which is this part, times this, minus sq times cosine of 2 pi f ct and sine of 2 pi f ct, which is this part. But this equation, I can write it as this, where I have used the trigonometric identities. Cos square is 1/2 of 1 minus cosine of 2 times theta. And cos theta sine theta is 1/2 of sine 2 theta. So the second line I have obtained from this first line by using those trigonometry identities. But this is actually equal to S of I. And the reason why is because sine of 4 pi f ct integrated over symbol duration, where fc is much greater than 1 over t of s, and similarly cosine of 4 pi f of ct, 4 pi f ct, again integrated over symbol duration, they both are 0. The reason I can do that is I'm assuming that si and sq are constants, so I'm pulling it out of integral, assuming that they don't change with time. And so when this term and this term, they both become 0, then all that I'm left with is S of I. So I got, from S of t, I got S of I. One other thing that I want to notice is that this cosine of 2 pi f ct, sine of 2 pi f ct, if I consider them together, integrated from 0 to 2, 0 to symbol duration, their product turns out to be 0. So it is as if this cosine and sine, if I think of them as vectors, and this operation, if I think of it as a dot product, and this is something that we have done in lab number 5, uh, where we actually did the Fourier transformation operation and we thought of it as a dot product. Similarly, this equation here, I can think of it as a dot product, vector dot product between vector cosine and vector sine at the same frequency. Then this vector dot product, as we are seeing here, is turning out to be 0. And you know that when the dot product between two vectors is 0, those two vectors are perpendicular to each other. The angle between them is 90 degrees. And so this sine, I'm going to call it quadrature signal. This cosine, I'm going to call it in phase signal. And therefore, I will draw these two as two mutually perpendicular axes. That forms our two-dimensional IQ plane on which we drew the constellation points. Okay, now that we understand how to extract S of I from S of t, we can follow the same type of derivation steps and show that if I, instead of multiplying by cosine of 2 pi f ct, if I multiply S of t with sine of 2 pi f of ct, then I'll get S of q back. So uh, essentially I have taken a signal which was at some high carrier frequency f of c, and I down converted it back to baseband, and I got the baseband signals Si and Sq back. Okay, So the last slide of this topic, and probably the last slide of this semester, I don't think that we will be doing the topic of quantization, mainly because I think we are running out of time. The semester is concluding. So I have already prepared the slides for the quantization topic, but I will not include it in the syllabus of the final exam. Uh, so this is the last slide of the modulation topic, uh, and also the last slide of CT 111, the entire semester. And this is probably the last that you will hear from me. Um, so let us conclude this topic, and also let us conclude the semester. Um, just like what we said about the timing estimation, that the receiver has to somehow figure out the optimal sample timing, and it's a big job. Um, it's an entirely new, different subject which we are not even addressing. Similar to that, the receiver has to also be able to generate f cosine and sine at the exact frequency f of c. Uh, that is also a big job. And in fact, there will be always some frequency offset. If f of c is, let us say, 1 megahertz at the transmitter, at the receiver it may be 1 megahertz plus 100 hertz, for example. The receiver may not be exactly able to synchronize with the transmitter. And so when the receiver thinks that it has generated the sinusoidal signals at 1 megahertz, compared to the sinusoidal signal at the transmitter, there may be some offset of 100 hertz or sometimes even more than 100 hertz. But not only that, the receiver has to generate cosine and sine at the right frequency, but also the phase has to be zero. There shouldn't be any phase here as well. So that frequency alignment and phase alignment at the receiver is also a big design task, and it's a separate topic, a technical topic by itself. So I will give you this homework that uh, I will ask you to do this derivation here, but instead of assuming that the receiver has exact cosine of 2 pi fct signal that the transmitter is used, assume that at the receiver this down conversion process has a small phase offset that I have denoted here as phi. So in presence of this phase offset, how will the receiver work? What will happen to this down converted signal? Will it be SI or it will be something else? Here, whether it will be SQ or it will be something else is what this homework question asks you to do. And there, all you have to do is apply some trigonometric identity. Okay, so just bear with me. I'll be back in a moment, and we will conclude this particular set of slides. Okay, so this is the end of the semester. CT 111 ends here. Um, the modulation topic has been concluded here. Um, Let us see. I will actually give you one lab, the final lab of the semester, in which I will ask you to um, work on the modulation in MATLAB. So that is one major exercise that you will be doing before I will let you go. Obviously, there will be end of the semester exam, so I will ask you to be prepared for that. I hope you have had good time in studying the content of CT111. A few things that I told you at the start of the semester, I will want to recap again. Uh, One thing is that as you progress further in your studies at this institute, um, do not be influenced by rumors or do not be influenced by the culture. I think have your own moral compass. One thing that I wanted to say in that context is that if your friends or if the if your peers are telling you that the communication theory is is not a subject to be focused on, the machine learning is, for example, the today's buzzword, then you make your own judgment. What I, I have tried to convey to you in this course is that many of the topics which are integral to communication theory, um, such as Fourier transformation, such as channel encoding, channel decoding, such as data compression, source compression, and especially the algorithmic method of data compression. Even these topics of modulation and demodulation, the underlying algorithms that allow all of these individual blocks that we have studied over past several months to operate, those underlying algorithms are integral to machine learning and artificial intelligence. You cannot not study signal processing and still hope to be a very good, uh, competent ML or AI engineer. So do not downplay the importance of the topics that we have covered in this semester. Um, all the way from ranging from estimation and detection, all the way from Bayesian theories, um, down to even the entropy function that we have studied in context of information theory. Um, the Viterbi algorithm that you studied in context of channel decoding, and some of you implemented BCJR algorithm, which is actually we are getting super close to, or actually that algorithm is very much firmly in the community of ML and AI, and so is Viterbi algorithm as well. And so all the topics that we have studied, the Fourier transformation is an integral part of JPEG standard, as um, one of the videos that I had mentioned on our Google Classroom had mentioned. The professor there, Dr. Gilbert Strang of MIT, is a very world-renowned professor, and he was talking about wavelet transform. And the way you can study wavelet transform and appreciate wavelet transform is only if you have mastered the intricacies of Fourier transform and the FFT function and so on. So as you exit out of this course, I want you to keep in mind the overarching nature of these various topics that we have covered, and consider that these topics form the foundation of not only the communication systems, um, but ultimately as you progress through your academic career, some of you may go on to do PhD or postgraduate studies in general, MTech or MS, whether it is here at DICT or at some IIT or maybe even abroad. Uh, and then as you start getting into the corporate world, what you will find is that all of these different topics, communication theory, signal processing, machine learning, AI, software engineering, um, algorithmic design, even the data networking, etc. All of these different topics that you are studying as different silos, different subjects, different compartmentalized subjects with their own instructors, with their own labs, with clear cut boundaries and demarcations between the subjects. Uh, they all actually merge. Uh, there is no such boundary between one subject to the next as you start advancing in your academic and professional career. And so it will be imprudent to under emphasize or maybe even ignore one particular subject uh, and think that it is out of favor or out of fashion, so to speak. So that is the last message that I wanted to convey to you. Um, I told you at the beginning of the semester that writing a paper is your ultimate objective. And the work that some of you have done for this project on the channel coding uh, leaves me with no doubt that you can definitely put up a super nice paper, uh, maybe next year or sometime soon. And once you develop that objective and you work toward it and you accomplish that objective, uh, you will be playing in the high leagues. It's like you'll be graduating from state level championships and you'll be entering the national level championships. And if you do super good job of writing a paper, you'll be actually even competing at the Olympics level. Uh, you are now getting to a stage of your academic career where your performance in the exams, although it is critical for next several years, it will start mattering less and less. What will matter more is your performance in the type of project that you did, uh, the convolution coding and decoding project, and how you work through a complex problem, how you define your own problem and solve it in a manner that nobody else has done before. That will be your exam. It will not be some 2 hour or 3 hour closed room examination. It will be a continuous examination that will go on over months and sometimes over years. And if you perform well, ultimately it is this paper that you will have in your hand, which will be your badge of honor, which will prove that you can compete at the international level. So keep that uh, in your mind as you progress through your studies here. And then finally, as you progress through your studies here and subsequent to that, uh, the thing that I have told you at the beginning of the semester that you want to always keep with you is those four word sentence, which is that the honesty is the best policy. Um, and actually, it is not just that honesty is the best policy. You don't want to think of honesty as a policy because then it becomes a calculation matter. You're counting. Um, Rather than that, honesty is the best creed, it's the best motto, it's the best passion to have in the life. Not honesty only in terms of what you say and what you speak, or even what you do, but honesty in your innermost thought uh, is what you should strive at. You should be honest at the internal most part of your mind and your heart, and that is an intangible value that I wish you always carry with you all throughout your uh, future careers. So, with that, I want to wish you all the best, and I hope that you do tremendously well, both academically and professionally. Okay, bye.